Thank you very much, Allison. I appreciate it. So when I wrote the abstract for this talk, I was pretty ambitious. And then I realized that it took me 9 months to write my PhD, and the thing was like 250 pages long. So even though I, in my abstract, anticipated being able to talk about my entire thesis, I'll probably give a slightly constrained overview today. But there's a lot to say, and hopefully I can get through it in enough time. But thanks, everyone, for coming today. The topic is there. As Allison noted, I was supervising my thesis by Gavin and Peter and Supriya, and I thank them for their assistance, even though they're not all here today, but Supriya's here, so that's great. In my talk today, I'm going to be talking a little bit about solar cell efficiency limits by way of just introducing the notion and the framework in which we can look at things like limiting efficiencies of conventional PV and other types of devices. And then really motivating the discussion of upconversion as a third-generation technique for increasing solar cell limiting efficiency. We'll be talking about the limits of upconversion devices, and then extending the typical models to a more generalized, realistic version of a silicon solar cell coupled to an upconverting device. And then looking at a generalized, realistic upconverting material in addition to a realistic solar cell. I think these things have pretty significant implications for experimental study in this field, and I'm going to outline that. And then talk, hopefully briefly, about enhancing upconversion processes in multilayer photonic structures, and in particular in erbium-doped porous silicon. So the detailed balance analysis is a framework for understanding the limiting efficiency of solar cells. Shockley and Queisser wrote a paper in 1961 that had an insight that any solar cell that's going to work at the theoretical limit will operate by converting photons to electrons, but it'll also be an emitter of photons, and it'll do it like a theoretical blackbody. And a blackbody emitter, as some of you may know, is described by Planck's generalized law, which is just a formula here, where it says that the photocurrent corresponding to the emission, blackbody emission from a solar cell, is basically proportional to a lot of things that we are familiar with, like Planck's constant and the speed of light and energy. But it's also proportional to the temperature of a solar cell, the voltage applied to the terminals, and this thing, epsilon, which is the étendue of a solar cell. And that describes the distribution of light coming out of the solar cell, the kind of geometric distribution. And so that's really the way we can understand how good a solar cell can be, a conventional device, as a photovoltaic converter. So basically, for a known solar flux that corresponds to this symbol here, the limiting photocurrent can be found at any applied voltage if we know the temperature of the solar cell. And it really is just the difference between what comes in from the sun and what's emitted according to this expression here. That's what we'll go through out of the terminals and through the external circuit. And from that, we can just determine that the limiting efficiency is determined by the maximum power point divided by the input power from the sun. So that's pretty basic stuff for probably most people here, but it is a public lecture, so I figured I'd go through that. So the limiting efficiency of a solar cell under, say, the AM 1.5G spectrum is really determined by the fact that in the Shockley-Queisser analysis, there's a perfect cutoff of absorption. So if a photon has a higher energy than the band gap, it's absorbed in the solar cell, and if it's got a lower energy, then it's not. And that's basically it. If we assume that it's at ambient temperature and it has non-degenerate doping, then really the efficiency is just a function of the band gap, with a few other things that we could talk about. But the interesting relationship is between the efficiency and the band gap. And it's shown here, in particular, from a recent paper by Martin, where he calculated the conventional efficiency limits for the new revised spectrum. And so what we see in the solid line is the Shockley-Queisser limit for a conventional solar cell under the terrestrial spectrum. And then these other curves that really correspond to the same thing but calculated with worse radiative efficiency. So really, of course, the theoretical limit is going to come when the thing has a perfect quantum efficiency. Any recombination within the cell emits a photon rather than dissipating that energy by non-radiative mechanisms. But it's worth looking at what happens when you have 1% radiative efficiency and even lower. And that's those dashed curves there. And you can see that these dots show how good these are kind of the best laboratory efficiency of solar cells made of crystalline silicon, gallium arsenide, and so on. And the silicon and gallium arsenide are getting close to pushing the radiative limit well, at the limit at 1% radiative efficiency, and they may actually be doing slightly better. But that's really where we're operating, is that silicon and gallium arsenide are both pretty ideal with the maximum efficiencies of about 33%. Now, the question that motivates third generation photovoltaics is, okay, 33% is great, and it would be great to get a conventional device operating close to that. But why isn't it more? Why isn't the limiting efficiency more? Well, for one reason, as we're all aware, sub-bandgap transmission corresponds to quite a large loss. So for the fact that I'm in third generation means that I'm contractually obliged to show this figure. But you may recognize that it kind of outlines all the loss mechanisms in a conventional device. But the one I'm really interested in looking at is this one here, the transmission through the solar cell of portions of the solar spectrum. For crystalline silicon, this sub-bandgap transmission corresponds to a loss of 19.1% of the incident power density. So it'd be great to be able to reclaim that somehow. Of course, we could lower the bandgap and collect more photons, but this also reduces VOC and it reduces efficiency. The previous efficiency curve shows that we can't do much better than silicon, actually. It's 33% under the 1.5 G spectrum, so we really don't want to reduce the bandgap. So upconversion is a device concept that's been proposed to actually modify the incident spectrum, convert sub-bandgap photons into photons that can be absorbed by the solar cell. Now this could mean many things, but the main concept is really doing this, breaking the Shockley-Queisser limit without altering the voltage of the solar cell, changes the spectral response of the solar cell itself. And we would do this in something like a luminescent layer behind a conventional solar cell. So here's the kind of structural cross-section where you have a solar cell without a rear reflector or a selective reflector perhaps, an upconverting layer and a reflector behind that. So anything that's transmitted through the solar cell is intercepted by the upconverting layer. And then in that upconverting layer, a 2-photon absorption process gives you, see, there's a stepwise sequential absorption process that recombines by emitting a photon above the bandgap or near the bandgap, thereby giving you at least 1 electron for 2 photons, which would have otherwise been wasted. Now, this upconversion process is not magic. It happens in rare earth ions and metal organic dyes. And the question is, how can we use this in a way that we can build a third-generation device that we can apply to a standard commercial solar cell production line? I mean, as you can see, we're not actually doing anything with the solar cell aside from leaving off the rear reflector. We're really just adding something additional on. So it's inherently attractive. Now, in 2002, Torsten and Martin and Peter Würfel carried out a detailed balance analysis of an upconverting device, a theoretical device. And they based their analysis on the Shockley-Queisser detailed balance analysis. But they used this 4-diode structure where the solar cell itself was modeled as a diode in the same way as in the Shockley-Queisser analysis. But anything that was below the solar cell bandgap was transmitted to this upconverting layer equivalent circuit. So in that circuit, you have 3 single threshold solar cells, in addition to this one making 4, all acting as black body converters. C3 and C4 are small bandgap cells that correspond to the 2 low energy transitions. And C2 corresponds to the emission of a high bandgap photon into the solar cell. You can see that the sizes imply that these have approximately the same bandgap. So basically what we've got back here is, you can think of it as 2 small bandgap solar cells putting an LED into forward bias such that it emits into the solar cell itself, which does the charge separation and charge extraction. Now in this, it's basically the same framework as the Shockley-Queisser analysis of the single junction conventional cell, but here you have to take into account a few extra things like photon emission between the cells and current and voltage constraints and matching. But that's basically it. It's not terribly complicated, and you can see how the energy, this kind of energy band diagram would come out of that analysis, but it's not really worth looking at in detail at this point. So when you do this with the AM 1.5 G spectrum, the new revision, you see that there's actually quite a large efficiency gain to be grabbed from this kind of a device. So these dark squares correspond to the single junction conventional limit. And these open circles are the upconversion limiting efficiency. The dashed line is just the percent gain efficiency increase by using upconversion. So what's circled there is crystalline silicon. And you can see that the limiting efficiency of a crystalline silicon cell increases from 33% to about 40% under the AM1.5G spectrum for an ideal upconverter coupled to an ideal silicon solar cell. So the standard assumptions of that analysis, the one that Torsten and Martin and Peter carried out, was, as I say, just an extension of the standard Shockley quasar analysis to a 4-diode model. One, the solar cell absorption is perfect in every case. For all the diodes, it's that step function 0, 1 absorption. Two, everything is perfectly radiatively efficient. You can add in non-radiative mechanisms if you like, but that's the assumption that was made to come up with those numbers, which is consistent with the notion of limiting efficiency. Three, and this is important, the upconverting layer has the capability of absorbing everything in the sub-band gap region, just the entire broadband near infrared for the case of silicon. And the fourth one is that the absorption of the two sub-band gap solar cells is selective, meaning they absorb over different portions of the sub-band gap spectrum. They're proximate portions, but they're different portions. They don't overlap, basically. But as we know, real solar cells don't behave anything like 1 or 2. They don't have step function absorption profiles, and they're not radiatively efficient, or they don't have 100% quantum efficiency. So is there a way that we can simply incorporate non-ideal absorption and non-radiative efficiency, as you see in the real device, into the upconversion detailed balance analysis in a way that's generalizable? At least I thought that was an interesting question, so let's see if you think so. So I think that you can do this simply by altering the optical model that you use in a detailed balance analysis. So starting with the tabulated complex refractive index data for planar intrinsic silicon, we can go all the way to the absorption characteristics of that material just by the Fresnel equations. So this is not terribly mysterious. Where we have the real and imaginary parts of the silicon refractive index, we can come up with a reflectivity, an absorption coefficient, and the absorption for any material with a thickness of D. And of course, it's subject to dispersion. It's based on it's got a wavelength dependence. And I used Mark and Martin's refractive index data from a paper in 1995. So from this, I wanted to generalize a realistic solar cell, and not from something like a PC1B model or an actual solar cell that I found in the literature. I really tried to think through what the optical design features of a normal solar cell are. So you can modify the absorption expression to account for a few things. One is just the thickness of a solar cell. So I took a very thick solar cell. Second is reasonable broadband anti-reflection coating. So planar polysilicon is quite reflective, but we all know that we add an anti-reflection coating or do other things to reduce the reflectivity in a real solar cell. You can do that just by modifying the R. Third is surface texturing or light trapping. Now this, in some sense, modifies D, the thickness, the effective thickness of the solar cell, by changing the optical path length, the average optical path length. However, if you think about what we're trying to do, we're still trying to take advantage of the fact that a solar cell transmits near infrared light. If you look at try to see the transmission of a heavily textured solar cell, everything gets stopped. Everything winds up being trapped in the solar cell until the point that it's absorbed by free carrier absorption and heats up the solar cell. So actually, you don't want extensive light trapping in a solar cell if you're trying to design an upconverting device. So I tried to account for just moderate light trapping. And then again, free carrier absorption is something that's not typically taken into account. However, when you are considering light trapping and doping that is non-intrinsic silicon, it actually plays a pretty significant role. So this is absorption that doesn't contribute to photocurrent, but does sap the photocurrent from a potential upconverting layer. So 10 to the 17th is let's say a standard or reasonable doping. And it turns out that that's a good thing. So the way that you factor in free carrier absorption is just by adding another term to the absorption coefficient there. This term is here's a model pulled out from literature from a Paul Bossor paper, Christopher Caresti's paper last year. It's got this term that's not KFC, that's that guy. It's kappa FC, and it has this value according to this paper by Chris. I'm just not going to touch that. So it's simple to include a broadband kind of non-selective anti-reflection coating. Again, this may not be particularly realistic, but it does sort of produce an average anti-reflection property. So we have a factor rho that simulates an ARC. Basically, it has the effect of suppressing reflection and boosting absorption, as you can see. And this is the sub-band gap region, or the region near the band gap. So you can see with this model, this refractive index data, there's actually some sub-band gap absorption, well beyond 1100. But it's not particularly sensitive to anti-reflection coating. Second is light trapping. In this case, with no free carrier absorption, you can see light trapping has the effect of just pushing out the edge of the absorption band beyond, and you can actually get substantial absorption beyond the nominal band edge of silicon, where 4n is the light trapping limit. Then factoring in free carrier absorption, you can have a look at the dependence of free carrier absorption on n, which is the material doping. And you can see that for 10 to the 16th, free carrier absorption is pretty negligible in the near infrared, but as you go to 10 to the 17th, it jumps up quite a bit. And then kind of at this inflection point at 10 to the 18th, so this is at 1500 nanometers, for example, it starts to rocket up. So this really indicates that you wouldn't want high doping. For ignoring any other reason, you wouldn't want a heavily doped base. It would make a terrible upconverter device to have substantial doping in the base. And then there's an interaction between light trapping and free carrier absorption, as I mentioned before. So when you look at light trapping with free carrier absorption taken into account, you can see that light trapping also enhances free carrier absorption. So this is why solar cells with extensive light trapping heat up. And that's, again, at 10 to the 17th. So this is the kind of absorption profile that comes out of that. Again, it's very generalized. Small variations from this picture, you can use many techniques to produce this kind of an absorption profile, but the dashed line is the Shockley-Queisser ideal absorption efficiency or absorption profile, and the solid one is the one developed with this generalized model. And it's plotted just against the solar spectrum for comparison. So how does it stack up in terms of the single junction Shockley-Queisser limit? Well, this is a plot of the limiting efficiency of a single junction device against the radiative efficiency of the device. So what we can see is that, this thing here, FREC, is actually the reciprocal of the radiative efficiency, so that this is 100% radiative efficiency and this is terrible radiative efficiency. So as one, the obvious thing is that as your quantum efficiency goes down, so does the efficiency of your solar cell. Second, I put the Pearl efficiency on there just to illustrate that at the point 10% radiative efficiency, which let's assume that's a good estimate of how radiatively efficient the Pearl cell is, this model still overestimates the efficiency a bit, but it's not too bad. And importantly, it provides a distinction from the ideal case. So how does it work out in terms of the limiting efficiency itself of the upconverting device? So looking back at the ideal case, where both the solar cell and the upconverter were ideal, we had 33% without an upconverter, 40% with an upconverter, which is a 21% relative increase. For a realistic solar cell with an ideal upconverter, where the radiative efficiency of everything is 100%, the solar cell peak efficiency drops to 30.5%, but the upconverter efficiency goes up to 38.5%. And this is a relative increase of 26%. And you get a similar result for a realistic solar cell with 10% efficiency, radiative efficiency, I mean, and an ideal upconverter. 26% peak efficiency for the solar cell, 32% upconverting efficiency, that's 23% radiative relative increase. So you can see that, interestingly, an ideal upconverter does better for a more realistic solar cell than for the ideal case. It may not be terribly surprising, but I think it is interesting. So that taken into account, that kind of explores the parameter space of altering the solar cell. But what happens when we start to consider the difference, the deviation between the ideal picture and the realistic picture for the upconverting material itself? Any crystalline silicon solar cell upconverting device essentially is based on erbium doping. So erbium-doped phosphors are really the most widely used, experimentally anyway. It's not of course not a production device, but from an experimental perspective, erbium, the rare earth ion, is used to attempt to increase the efficiency of crystalline silicon solar cells. And the reason is pretty obvious. These two things are both erbium just erbium ions. One's labeled D and A for donor and acceptor. And what we show here is just an energy transfer process that allows upconversion to occur in erbium. So erbium, like most rare earth ions, is distinguished by these really discrete energy levels that kind of go up in a ladder and don't change very much based on the host. And erbium absorbs, this first excited state transition is at about 1520 nanometers. And then there's this transition from 4i 13 over 2 to 4i 9 over 2 is about the same energetic distance. So that if you have two closely spaced erbium ions and they both absorb a 1520 nanometer photon, one can donate its energy to the other, bumping up the excitation state of the acceptor ion. And energetically, it just works out that it's quite likely that it will be de-excited through a non-radiative small energetic loss, and then a big step down back to the ground state that emits a 980 nanometer photon. So this is very interesting for crystalline silicon because it absorbs below the band gap and emits above the band gap, and it's quite likely to do so. But you can see it's pretty different to the notion of broadly absorbing upconverting materials like the one that's modeled in the ideal case. What we have here is the absorption spectrum of erbium in this part of the spectrum, from 500 nanometers to 1600 nanometers. So again, this is where the upconversion of interest would occur. We would be absorbing photons down here and looking for emission from this line here around 980 nanometers. You can see this absorption band here is, it's reasonably wide. It's more than 100 nanometers wide. But it's a lot different to the notion of being able to absorb every single photon in the sub-band gap region. So it's not broadband absorption. And secondly, it's not selective. I just described two ions absorbing the same type of photon, not two ions absorbing photons in neighboring regions of the sub-band gap spectrum. And third, it's not complete. It's actually a quite weak absorber. Erbium ions have very small absorption cross-sections. So we really have to factor in these things when we're considering how a realistic erbium-based material is going to perform. So what I'm proposing is to sort of rely on an idealized erbium absorption. It's still ideal in the sense that it's possible to absorb every photon in the sub-band gap spectrum. But it's not ideal in the sense that it only absorbs over a realistic portion of the solar spectrum, 1450 to 1650 nanometers here. And it's actually, I'll be modeling it by two small band gap solar cells with the same band gap, which is really much more like the real erbium absorption would be. Two solar cells that absorb over the same spectral range. And note here that the absorption only goes up to 0.5. The point is that at 0.5, an absorption of 0.5 per ion, every single photon in the sub-band gap spectrum is absorbed. Because they overlap, a single photon of, say, 1500 nanometers, when it's guaranteed to be absorbed, will either be absorbed in one erbium ion or the other. So a 0.5 absorption actually corresponds to complete absorption. If that's confusing, think back to the actual model where we had two solar cells. For a single photon coming in, it's either got to go to one or the other. So it has a 0.5 50% probability of being absorbed in either one. And the important thing is that even though this is a kind of flat trend, it's meant to be an average over all the wavelengths. So you can pick any kind of line shape that you want. It's going to be of diminishing applicability because the difference is going to be pretty slim anyway. And the other thing you have to take into account is idealized erbium emission. It's also a narrowband emission line stretching from about 930 to 1050. And I just assumed that the emissivity is linked to the absorptivity. So if the erbium absorbs well, then it emits identically. So for absorption of 1, that means that every photon in the sub-band gap region was also absorbed. In the model, all the other detailed balance constraints are enforced. There's no other difference. So what happens when you run the efficiency calculation is this. You see that for example, a 10% radiatively efficient solar cell and a 100% radiatively efficient upconverting layer, the the benefit from upconversion is pretty slim. So down here we have the one sun result. At zero absorption, which is effectively no upconverting layer, it's 26%, which we saw previously. And as you go out to total absorption of every photon within this spectral range, the limiting efficiency only goes up to about 26.5%. And that's the limiting efficiency, not the real efficiency. It's interesting that there doesn't seem to be any additional benefit by having concentration in this case. Of course, you get a higher efficiency overall, but you can see the slope of every one of these lines is just about the same. This is in the case of a 100% radiative efficiency in the upconverter. For realistic radiative efficiencies, concentration helps quite a lot. So what does it mean to have this trend with regard to a realistic upconverting material like sodium yttrium fluoride doped with erbium? Well, let's say we wanted to get 1% boost of the efficiency. That means we need, say, 0.25, like 25% absorption per ion, or 50% absorption, half the photons that come in get absorbed. Well, for that case, just going from the absorption coefficient, here we have the absorption per pair of ions, go down to the x-axis in the path length, and you'll see that we need something like 5 millimeters of phosphor material to get to that point. But again, that's only 1% relative, or 1% absolute efficiency increase for the ideal case. So one way to improve this, this consequence is to consider broadening out the erbium absorption spectrum. Now, we can't do that with erbium itself, but there's potential for a concept where we can have broadband absorption in some kind of sensitizer molecule or quantum dot or whatever it might be that donates its energy to the erbium. So as we saw, erbium has a very narrow absorption spectrum. If we can couple it to something that has a broad absorption spectrum that can absorb, say, at 1180 nanometers and then downshift that energy and sort of funnel it into erbium, then maybe we can see some benefit to the overall efficiency of the upconverter. Lead selenide quantum dots have the potential to do this kind of thing. There's a good paper that shows that you can have absorption in this sort of spectral region that we're interested in and emission down at 1550. So that's this dashed line here is a conceptual downshifted absorption spectrum where we've now broadened out the absorption and can absorb all of these photons, but they're still just pumped in to the intrinsic erbium line. And so how do we fare in that case? Well, again, with all the other things being held constant, with downshifting, you actually see a pretty substantial boost to the efficiency, which isn't surprising. We're absorbing many more photons in this case. So again, for the one sun case, we can look at an increase down here going from 26% now up to about 30% when we have complete absorption in this combined sensitizer upconverter material, which is good. And it's interesting that this increasing the concentration to the limit actually gives you a bigger step. So here we have something like a 5.5% absolute increase in the efficiency compared to about 4 here. So to summarize all that stuff, there have been no reports of increased crystalline silicon efficiency from erbium-based upconversion, not in any case. Even though there are quite a few experiments that have been looking into this. But the modified detailed balance really shows why. The limits from this are really quite modest. 1% absolute increase for 100% quantum efficiency. And that's for a perfectly absorbing upconversion layer with no downshifting, granted, but only 4% absolute increase for a layer with perfect downshifting. At full concentration, you get the same benefit if there's no downshifting. And that's for 100% external quantum efficiency in the upconverter. And with downshifting, you get quite a nice benefit, 5.5% absolute. And that's compared to 6.6% for the ideal upconverter with the non-ideal solar cell. So that's pretty substantial. But again, that's for perfect quantum efficiency. And it does illustrate what we would need to do to an upconverter to really have effective designs for upconverting materials. One, they have to incorporate an enhancement of the absorption, of the intrinsic absorption. And two, downshifting appears to be key to designing an appropriate device. And just bear in mind that this all goes out the window when you consider realistic radiative properties. So what are some methods to enhance absorption? This is really what I wound up looking at in my thesis. This, is really very schematic way. This is like if I wind up getting a Nature paper, we can put this kind of lame junk in there. This is normal absorption in a block of, say, phosphor material. Of course, we can just have more material. We've seen that, and that's obvious. We can put a mirror on the back, and it's effectively like having twice the thickness of material if the mirror is perfect. There are a lot of interesting proposals to add gratings or plasmonic kind of structures at the rear or at the front of such a material, and that couples the incident light into like waveguide modes and so on, and essentially gives you quite an increased path length. What I'm going to talk about now is represented by this kind of little schematic, where we can actually structure an upconverting material in such a way that it produces a resonator. It's a wavelength selective resonator, but it's something like a cavity effect, where we essentially increase the internal field intensity, illustrated by this nifty little exploding arrow, increase the internal field intensity, and therefore increase the interaction between the incident light and the upconverting material. And the material we've proposed to do this in, or that we did for these experiments, was erbium-doped porous silicon. Porous silicon is formed from crystalline silicon by etching it in a HF solution anotically, so it's an electrochemical process. It produces a porous but quite stable silicon skeleton with a very large internal surface area. And the kind of porous silicon we were looking at has pores on the order of 100 nanometers in diameter. So porous silicon offers some interesting properties. One, it's got a tunable refractive index. So the porosity, the refractive index is inversely proportional to the porosity. The more porous you make it, the lower the refractive index. You can make quite uniform, high quality, thick layers. And you can actually stack these layers by just modifying or modulating the current as you etch. Because it's got a huge internal surface area and it's based on a conductive substrate, you can electroplate from solution and actually have quite a high concentration of dopants within the internal structure. And it was interesting. It was good because it allows for speedy, very simple prototyping. You do it at room temperature. There's no vacuum. It's quite advantageous to other types of deposition processes. So here's some kind of representative results of upconversion photoluminescence measurements from porous silicon erbium layer. So we electroplated from a saturated erbium chloride ethanol solution into a thick layer, 43%, and nearly 6 microns thick. Annealed it in this process, and you need to do this to optically activate the erbium that's within the structure. And we saw, under 1550 nanometer laser excitation, a very distinctive erbium upconversion emission spectrum. So if you think back to the ladder diagram, what we have here is emission at 550, 660, 810, and 980 nanometers. But you can see the excitation power is quite high, and I just take it from me that these are weak lines. So what we have is a not very efficient upconverting material, but an interesting basis for investigating photonic upconversion enhancement by structuring it in this kind of way that I described. So you can make something like a distributed Bragg reflector with porous silicon, again, by just modulating the current density as you etch. So what we have here is a 30 bilayer structure. You can produce, there's plenty of literature on high quality optical structures like dielectric mirrors, microcavities, and so on, just by doing etching in this modulated way. Again, having a periodic porosity, which comes from having periodic etching current, gives you a periodic refractive index. And you can see this is up close of high magnification image of just a few layers, a difference in density between the layers. And with a periodic refractive index, you get something like a mirror. As you see here, these are reflectivity profiles of this very structure. And there's a wide band of quite high reflectivity. It's interesting, you can also tune the optical properties of this thing after you fabricated it, like by oxidizing it slightly. So you can see the band shifts to the blue and contracts a bit as the mean refractive index is lowered. So it's very handy for a lot of things. The design of the structures just relies on having a suitable effective medium approximation. But you can design structures in a pretty predictable fashion. So it's a useful analogy to think of one of these dielectric multilayer stacks as some kind of a photonic crystal. Now, in the case of an infinite stack of modulating refractive indices, you can say that the thing has something like a band structure. So as soon as you have a contrast between two refractive indices in a periodic lattice, a photonic band gap starts to arise. So what we have here is band structures of the same kind of distributed Bragg reflector, but with an increasing contrast between the refractive indices of both layers. So here this is 1, meaning it's the same refractive index, and we just have normal dispersion based on a single refractive index. But as you increase the contrast between the layers, you can see that here at the edge of the Brillouin zone, a small band gap begins to open. This is exactly like you would see for electrons in a periodic potential. As we go to 2.5 and 3.57, that band gap gets bigger and bigger. Now down here in velocity space, we're plotting the phase velocity and the group velocity within the same structure. And that's just the ratio, the omega over k of the band, and then the derivative of that. And we can see that for no refractive index contrast, there's no change in either the phase or the group velocity. But as soon as we open a band gap, you see two things happen. One is that the phase velocity begins to decrease at the edge of the Brillouin zone. But the other, and the more interesting one, I think, is that the group velocity plummets towards 0 at the edge of the Brillouin zone. And that happens to a greater and greater extent with the increase in refractive index contrast. So the group velocity is the propagation velocity of energy through the structure. So it's possible for that to be 0. It's not really possible for the phase velocity to be 0. That's an infinite refractive index. What happens in the case of a finite material? That was all infinite. Well, in this case, we can talk about the reflectivity spectrum. And we've simulated that for porous silicon distributed Bragg reflectors with this refractive index contrast. One layer is 0.5, has 50% porosity, and the other is 70%. And I've fixed the band edge at 1550 nanometers. That's the strong absorption line for erbium, and it's also our laser wavelength for subsequent experiments. And you can do this with the transfer matrix calculation. WVAs is the same thing. And what we have here is a structure with 10 bilayers, high-low bilayers, 20, 30, and 40. And you can see as you go to greater and greater numbers of bilayers, you start to approach the infinite case, essentially. Your band edge becomes sharper. It actually becomes a little more narrow, and the fringes become compressed. So for an infinite case, you would just have the average of all these, and it would look like a continuous material. And the red line indicates the position of the band edge at 1550. So you may be interested in, or you might not, the question, what happens to the electric field when the group velocity becomes so low? Well, we've simulated, again, the same kind of a thing, but now done it in a few different dimensions. So we're going to be looking at the relative field intensity both as a function of depth into the structure and spectrally as a function of wavelength. So here for the n equals 10 case, which we saw previously, we're looking at the range between 1500 and 1600 nanometers. And you can see that throughout the structure, there's some kind of concentration of electric field around the band edge. But the maximum is only really 1.98, which isn't particularly interesting. So 1.98 relative to the incident field intensity from the outside. But as soon as you go to 20 bilayers, the internal field intensity around 1550 boosts up to 6.22 at the maximum, which is clearly right there, kind of in the middle, and in the middle. And then going to 30, 13.48, and at 40, 23.46 times the incident field intensity. And you can see, of course, as this happens, the enhanced region becomes squeezed smaller and smaller, and we get essentially an intense standing wave within that region of the first transmission point next to the band edge. So it's quite interesting. But the question is, can we somehow make the erbium interact with that high field intensity within a structure, within a real structure? And what can we gain by it? So what I've done, again, is trying to model this in a similar way. Take a Gaussian fit to an empirical erbium absorption coefficient profile. So this is, the solid line is one for sodium yttrium fluoride that was measured by Abi-Shalav, and the dashed line is just a simple Gaussian fit. Incorporate that into the refractive index data, and then resimulate a structure with all of those combined. So here, for example, is the n equals 10 case. So we have the real refractive index, the solid line, and then the imaginary refractive index that corresponds to erbium absorption. And that's the dashed gray line. And it's multiplied by quite a large number, 10 to the 5th, just so that you can see it be plotted on the same scale. But you can see that there's an inverse proportionality between the two. So as the refractive index in the silicon becomes lower, that is, as the porosity is higher, you actually have higher absorption in erbium. Because it's porous, we can essentially pack more erbium into a more porous layer. So simulating the absorption spectra of this kind of structure shows you how the erbium can interact with high fields. So first of all, the one with 10 bilayers that essentially had 0 field intensity enhancement. This is the baseline absorption, effectively. As we go to 20, you see, first of all, some enhancement of the peak height, going from 10 to the minus 3 to approaching 10 to the minus 2, and kind of the imprinting of the interference fringes on it. At 30 bilayers, we get an increase again to 10 to the minus 2 peak at 1550, and then it pushes up again for 40 bilayers above 10 to the minus 2. And it's logarithmic because it kind of shows you all of the interesting features. From that, we can produce an effective absorption coefficient. Now, the effective absorption coefficient allows you to discount the fact that for more bilayers, you have a thicker structure, effectively. So, of course, for a thicker structure, we can have more erbium. It's no surprise. But if you look at the absorption coefficient itself, or an effective absorption coefficient, then it kind of discounts that impact. So what we see here is the broadband average effective absorption coefficient based on that formula. For, on the left, the region between 1450 and 1650. The dashed lines are one bulk phosphor, so a porosity of 100% essentially. And this H80 is something that just corresponds to an undifferentiated porous silicon structure with a refractive index of, or a porosity of 0.6. So essentially the same material but with no photonic properties. So you can see that at 10 bilayers we have not much interesting to report, but as soon as you get to 20 and above, the effective absorption coefficient goes above the bulk value, which is quite interesting. Because again, this discounts the fact that you could have a thick layer. As you go to a huge number of bilayers, 100, you can see that there's a saturation. And so it's just as useful to really make a 40 bilayer structure as a 100 bilayer structure. And that's just because the enhancement region becomes so narrow that even though the peak height is huge, it's hard to access. If you look at the narrow band around 1550, you get an even bigger number, of course. And that number comes around between 30 and 40 bilayers and then drops off again. And that's mostly an artifact of a limited resolution in the simulation. But again, it's well above the bulk average, which is quite interesting. And so there's a clear relationship between the position of the band edge and the absorption in this stuff. So we can look at how all of that changes as you change, say, the incident angle. So for S polarization here, we can see that there's a blue shift in the interference features and the position of the band edge as you increase the incident angle from 0 to 32.5 degrees. So this is the reflection, the transmission, and over here the absorption. And it's pretty small. I was hoping it would be bigger, but these peaks increase quite a bit as that band edge point shifts to the blue. I'll quantify that in a sec. We also notice that there's actually a quite broad region of enhanced absorption. It's not like it's just at the band edge. So the wavelength selectivity actually isn't much of a barrier until you get up to the point where the photonic band gap has overlapped the absorption of erbium. So that's S polarization. There's splitting. P polarization has a different dependency. You can see that the shift in the features isn't as great to the blue as it is for the S polarization. And that's just because the polarizations see different refractive index structures as they're incident on the material when the angle is off the normal. But again, it's the same kind of phenomenon where you have a quite sharp peak when the band edge is overlapping the major features of the erbium spectrum. So this is just the kind of summed or the integrated area underneath the absorption curve in that region. This number is not particularly useful. It's some cumulative absorption figure, but it just does illustrate the dependence of the total absorption on the position of the band edge. So as we increase the angle, the band edge shifts and crosses the major portion of the erbium absorption spectrum and then drops off as the photonic band gap starts to cover it. The same appears to be true for P polarization, but I didn't continue the simulation out that far because it's not particularly interesting. So there's a clear trade-off between the slow light enhancement that you get by having the band edge in a particular position and the fact that right next to the band edge is the suppression of the photonic band gap. So it bears in mind, it pays to bear that in mind. So what's the effect of pumping erbium near the band edge of a real structure? Well, through kind of trial and error fabrication over quite a long time, we managed to make a structure that had a band edge near the 1550 nanometer mark. And again, that's the laser wavelength. It's also a strong absorption region of erbium. The major challenge that we found is that to make a structure like this, you have to oxidize it and subject it to high temperature processes, basically. This activates the erbium content and suppresses the refractive index a bit to let light out. But they severely degrade the structure. So this truly was trial and error in that sense. You can see that we have here, so this is a 27 degrees of incidence, P polarization, the reflectivity profile of such a structure. But it looks a bit more pathological than the nice simulated refractive index or reflectivity profiles. But it's still quite a high transition between the peak reflectivity and the kind of normal dispersion region down here. And again, there's the 1550 nanometer mark sitting right on the band edge between the high and the low reflectivity regions. So this is this sample here, etched according to this recipe. I'm short on time, so I'm just going to fly through that. It's got 30 bilayers, so it's a moderate kind of moderate thickness with a decent, in principle, a decent enhancement. So we carried out angular-dependent PL in this thing. So if you vary the angle of excitation, as we've seen, you vary the effective band edge position, and you can see this here for these reflectivity profiles. We go from 21 degrees, which is the black line, and blue shift to this position here for 37 degrees. And you can see that the band edge kind of traverses that 1550 nanometer point. What we'd like to see is, does this relate or correspond to a variation in the intensity of the PL that we see when we excite the thing at 1550 nanometers? And does it agree with the expected variation in absorption that we have modeled? So this is the system we set up. There's a laser on a rotation arm pointing at a fixed sample position on a goniometer, so we can measure the incident angle. And we collect PL normal to the sample in all cases. It goes into a little mini spectrometer, and Bruce Springsteen takes care of it over here in the computer. Darkness on the edge of town. I listened to that all the time when I was doing these measurements. Whoops. So we carried out UC upconversion photoluminescence at these angles here to correspond to this reflectivity diagram, and got a whole range of spectra like this. Excitation again at 1550 and at about 200 milliwatts in order to get anything out of these samples. Again, note the difference between the difference in intensity between the 980 nanometer peak and these guys here. So it's a single spot for this, average of 5 2.5 second acquisitions. The peak's also a bit cut off there at the end. We did our best. So looking at the normalized variation in the upconversion intensity for 5 spots that were 0.5 millimeters apart each on the sample, we tracked the PL trend per peak. So each peak was kind of considered an individual experiment. And they were each normalized to the weakest PL for that peak. So to look at the diagram, what you see is that the different transitions are labeled individually. So we followed the 550 nanometer peak and 660, 810, and 980. And they all seem to have a low PL there at 38 degrees. So everything's normalized to that. And when this says enhancement, it really just means the intensity relative to that point. It's not necessarily enhancement in the broad sense. So yeah, just to go back to it quickly, we see that 550 has actually quite a large variation over that region, nearly 26 times enhancement, around 34 degrees of incidence. The other ones are quite large as well. I mean, they're dwarfed by that guy, but between 5 and 10 times enhancement over this region. And there's a smaller peak at a shallower angle as well. So how does this correspond with the model? So looking at the strong 550 nanometer peak, because it's impressive, we can track the reflectivity for each angle. So this gives you, from the perspective of a 1550 nanometer photon, what does it see when it comes into the sample? Well, from reflectivity alone, you can't explain this variation. Because this point here is high reflectivity, this is low, and yet we have quite emissive erbium at that point. But you note that there are these weird little inflection points that seem to coincide with these enhancement points. So this is again for the real structure. Now, if we look at the model, the things that I showed before with the variation of the features with angle, you can see that as the reflectivity goes through these inflection points in the model, we have similar peak or enhancement of the absorption at 1550 nanometers. So they're not one-to-one because this is PL and that's absorption. But you can make a link between the two in your mind, but it doesn't have to be a tight link. However, there does seem to be some interesting, there's an interesting correspondence here between the fact that we have kind of non-monotonic behavior with regard to reflectivity and absorption or PL. So yeah, there are absorption peaks for reflectivity troughs. That's not a surprise. As the reflectivity goes down, absorption goes up. However, the absorption is clearly not dependent just on the reflectivity itself. For example, take this point here where we have, let's say, an enhancement of 14. There's an identical point here where the absorption is at this point around 8, and then crossing this line, another really low absorption. So it does appear to correspond to something else in addition to the absolute value of the reflectivity. So this reflectivity profile is not this reflectivity profile, clearly. There's quite a large difference between the two. But the fact that the laser was sampling a sub-millimeter point, while the reflectivity was sampling a quite large area on a sample that had some obvious inhomogeneity, means that this reflectivity profile could be quite smeared out compared to what the laser was essentially sampling when it was incident on the sample. So just run through some conclusions quickly. Remember way back in the beginning when I was talking about the detailed balance, it's not the best means for analyzing or predicting the real operational characteristics of devices. But if you place simple constraints on the detailed balance model, I think it kind of allows for straightforward comparison between the non-ideal and the ideal cases. So what we did was extend the classic Trupkean upconversion detailed balance analysis to the new AM1.5D spectrum. That was kind of a bonus. And to the generalized non-ideal crystalline silicon solar cell. We did that by incorporating anti-reflection coating and light trapping and free carrier absorption. Second, it was interesting to find that the ideal upconverter gives you a relatively bigger bang for your buck for a realistic crystalline silicon solar cell compared to the ideal case. Again, 26 or 23% against 21% for the ideal case. But you have to consider that the realistic cell that I was talking about has to have poor light trapping properties, which may ultimately just be a false economy. If you're going to suppress your light trapping in order to have upconversion, and only a little bit of upconversion in that case, you may not be benefiting. Like this doctor says to the fat guy, the day-old donuts may be a false economy. Think about that one. It's really hilarious. So, second, the idealized upconverter that we're really taking into consideration in the detailed balance is vastly different to a real upconverting material. Erbium-based upconverting phosphors that have narrow band absorption, they're poor absorbers. You can approximate these properties even in an idealized way where you can really boost the absorption, for example. You can incorporate those into the detailed balance model. And we saw as we increase the broadness of the spectrum, we could, again, approach the ideal case. But the fact is that the limiting efficiency of the realistic solar cell was only boosted by 1.5% by perfectly absorbing perfect quantum efficiency erbium-like upconversion material, regardless of the concentration ratio. That becomes 4% at 1 sun or 5.5% at a full concentration with downshifting. Really, it's no wonder that there are no reports of crystalline silicon upconversion photovoltaic enhancement. It shouldn't be surprising in that sense. Do you want impressive results? You should use a bad thin film solar cell, and then you can have impressive results. And in fact, I think the fact that upconversion has so little benefit for crystalline silicon shows how good crystalline silicon is as a material, thanks to generations of engineers and scientists improving it. So third, it seems that substantial absorption enhancement, I mean, not tremendous, but an interesting amount of enhancement is achievable in principle in one-dimensional photonic crystals, and that's only in one dimension. You can get higher numbers in 2 or 3 dimensions. So it seems that band edge modes where the group velocity goes to 0, we can get high internal field intensity tens of times, almost 100 times for a huge number of layers. And that we can increase the effective erbium absorption coefficient over the bulk value. There are other ways to do this too. It's not a unique, groundbreaking technology. So attempting to fabricate real structures had its challenges, of course, but we saw non-monotonic PL intensity with a variation in the band edge position, which is really what we were trying to look for. It's an indicator that something promising is happening, and it's promising for narrowband enhancement as well, for a whole range of applications. But it's inconclusive what exactly is driving it and what the real dynamics are in terms of things like saturation and so on. But I just want to thank you all for your attention. I'm sorry, I just nailed it, but just enough to not have you ask me any questions, so go away. No, thank you very much, I appreciate it.
Thanks, Greg, for an excellent talk. This room is booked after here, but I can't see anyone milling around, so I think we have got time for some questions.
All right, if you insist.
Is that any questions? By the way, I think Thorsten will be rapt to know he's become an adjunct.
Oh yeah, that's right. More ways than one.
I was wondering when you, well, thanks for the presentation.
Oh, thank you for listening.
But I was wondering when you were trying to make it more realistic and model, you still did not include Auger recombination, which we know reduces from the 33 to 29. So this 26 is still way overestimated. Is there any reason why you didn't include Auger if you were trying to make it more realistic?
No, there wasn't a good reason I didn't include it. I guess, well, I suppose from the perspective of optical properties, I was really trying to account for design. So if you take a piece of silicon and you do X and Y and Z to it, it doesn't account for the actual electronic properties of it. You can factor it into the detailed balance equation. I didn't do it. I could certainly extend it to do that. It would be even more depressing, I'm sure, to do so. But yeah, that would be another extension to it. And I can imagine there are quite a few other ones that I might take into account. But I guess in a sense, time prevented me from doing it. And I think to some extent, you begin to have diminishing generality when you factor in every little thing. So for example, I could have said, oh, no, we're going to have a realistic erbium line shape absorption instead of a broad band with an average enhancement. Of course, it would change because sampling of an average over what is a fluctuating background in terms of the solar spectrum means that you're picking up photons that you wouldn't otherwise and so on. So I think you can always improve on the specificity of these things.
Well, one of the reasons I was mentioning it because you point out that there's still something interesting because the pearl cell is still lower.
Yeah.
But it's
fair enough.
Lower because
Auger, yeah. Right? Yeah, that's a great point.
Any other questions? Actually, I've got one about your porous silicon Bragg reflector. So how did you actually get the layers in?
So I mean, it's an interesting process because you start with crystalline silicon, and as you etch down, when you etch the top layer. So the top layer that was in that image was the first layer that was etched. As you etch, you provide a pathway for HF to enter the structure, and then it etches selectively at the interface. So the top layer is essentially not etched anymore. It's depleted of holes that allow the etching to carry on. And all of the etching occurs at the HF silicon interface at the bottom of the pits actually. So that's why you get a really coherent, uniform structure. The porosity of the top layer winds up being approximately the porosity of the layer deep into it. So you etch from the top down. The first layer you etch is the top one, and the last you etch is the bottom one.
But what are the layers in between? How do you?
So one thing that you can't have is a layer of porous material and then a layer of crystalline silicon with no porosity, because you have to have each layer be porous to allow transport of the electrolyte. So, for example, the top layer was 50% porous. The second layer was 70% porous. The next one was 50% again. So as you go down, you essentially keep making pathways for HF to filter into the structure.
But how are you changing the porosity as you go down?
Just by changing the etching current.
And then so the pores must be continuous all the way through.
They, depending on so N-type silicon actually provides extremely straight pores, as long as you've kind of seeded them with, say, lithography or something to that effect. In P-type silicon, it's slightly different. They seem to kind of be spider-like and more spongy. So clearly there is a continuous path that you could draw, but it's not as obvious as finding one that goes straight down. They often branch, come together, coalesce. It's quite interesting
so
stuff.
How do you get the erbium into them?
So the erbium then is, you do the same process in reverse polarity with the substrate on a cathode and immersed in solution. And you electroplate, and the erbium simply diffuses into the pores in solution form and then deposits itself on the walls.
Deposits on the wall?
Yeah, not into the silicon. You can get it into the silicon by annealing to some extent. Yeah.
Any other questions? Okay, and that, thank you very much, Craig.
Thank you, Alice.
It was excellent talk.
Thank you, everyone.